Hello everyone, I welcome you all for the third session of Unsymmetrical fault numericals with respect to the synchronous generator terminals. Let us see the example 1. A three-phase generator with constant internal voltages gave the fault current values as 1.4 kA for line-to-line fault and 2.2 kA for the line-to-ground fault. If the source voltage is given as a 2000 volts and x1 is equal to 2 ohms, determine the reactances x2 and the x0 values. We don't have any fault impedance here. For line-to-line fault, we know this is the reactance x1, the voltage, EA value, x1 value, and this is the negative sequence reactance x2 value. These two will be connected parallel to each other, and this is the current IA1 and this is the current IA2. We know the fault current is equal to root 3 times of the IA1 value. IA1 value is equal to EA divided by x1 plus x2. So this can be written as the fault current will be a line current. So you can select, you can represent here directly the line voltage, that is 2000 volts divided by x1 is a 2 ohms plus the x2 value. So find out this. x2 is equal to root 3 times of 2000 divided by 1400 minus 2. So if we simplify this, we will be getting 0.474 ohms. So this is the required x2 value. Now we need to find out the x0 value. For that, they have given the line to ground fault data. There is a fault current of 2200 amperes in line to ground fault condition. If we take the line to ground fault, all the sequence networks will be connected in series with each other. Positive sequence, negative sequence reactance and the zero sequence reactance. We don't have any fault impedance. x1, x2 and the x0 values and the EA value plus minus, all the currents are equal, IA1, IA2, IA0 value. Therefore, the fault current IF is equal to 3 times of IA0, that we know. The fault current is given as a 2200 amperes is equal to 3 times of EA value is 2000 divided by x1 value is 2 ohms plus x2 value. Just now we have determined the x2 value as 0.474 ohms plus x0 value. That's it. If you simplify, the x0 value is equal to 60 by 22 minus 2.474. That will give us 0.253 ohms. Let us see the second example. A salient pole synchronous generator without dampers is rated 20 MVA 13.8 kV and has a direct axis subtransient reactance of 0.25 per unit. The negative and the zero sequence reactances are 0.35 and 0.1 per unit respectively. The neutral of the generator is solidly grounded. Determine the subtransient current in the generator and the line-to-line voltages for the subtransient conditions when a single line-to-ground fault occurs at the generator terminals with the generator operating unloaded at rated voltage. Neglect the resistance. Looks to be a very lengthy problem, but it is a direct problem. Only a little bit of extension they have given. Let us see what is that. If you look at the given data, we know the MVA base value, kV base value, direct axis subtransient reactance XT double dash 0.25 per unit, and the negative and the zero sequence reactances have provided. The negative sequence reactance is 0.35 per unit and the zero sequence reactance is given as 0.1 per unit. The neutral of the generator is solidly grounded. Determine the subtransient current. So they are asking us to find out the subtransient current in the generator and the line-to-line voltages VA, VB and VC we have to find out for subtransient condition only when a single line to ground fault occurs. What does that mean? The subtransient current is nothing but the fault current, and we need to find out the line voltages also whenever the system is subjected to the single line to ground fault. Now we are studying this fault at the terminals of the synchronous generator under no load condition. Now the concept is as usual, so we are going to find the fault current with respect to the synchronous generator, and it is a single line to ground fault. All the sequence networks will be connected in series. So all the sequence currents will be equal in the series circuit. IA0 is equal to IA1 is equal to IA2. And we know the formula for fault current also, that is 3 times of the Ia naught. Only we should look at what will be the procedure to find out the line to line voltages in this condition. First, let us finish the part 1, that is finding the fault current. So if you look at the fault current equation, that is 3 times of Ia naught. Ia naught is equal to Ea divided by x1 plus x2 plus x naught. You know that where the x1 is given, this xt double dash is nothing but x1. The direct axis subtransient reactance will be called as a positive sequence reactance for the generator. Now, this Ea value is given in terms of the volts, that is a kilovolt. They have given Ea is equal to 13.8 kilovolt. And we know x1, x2, x0 values are given in terms of the per unit. To find out the fault current, either we have to convert this voltage to the per unit value, or either you have to convert these reactance values to the ohms. Then only you can proceed. That means the numerator and the denominator both should be in the same units. Either it should be both in per unit values, or either it should be in their respective units. If one is in per unit, one is in actual unit, means we cannot proceed for any further calculations. Now, which one we have to preferably consider? Whether we have to convert the reactances to the ohms, or whether we have to convert the voltage to the per unit value, means depending on the problem. If they have asked you only to find out the fault current, so that is easy for us, because the fault current, first if you convert this voltage alone to the per unit, that is sufficient. We know the voltage Ea is equal to 13.8 kV. This is a rated voltage. Whatever the rated voltage in the per unit, we will assume the rated voltage is equal to 1 per unit. So directly this Ea value can be replaced by 1. Then directly you can add all these values in terms of the per unit. In one step you will get the fault current, If in per unit. If you want to convert this into amperes, then find out the base current from these two values. By using the formula I is equal to MVA base by root 3 times of kV base, you will get the base current. Then you can find out the actual value is equal to per unit value into base value. But here the problem is not going to end with this fault current. So we have to find out the line to line voltages also. So what does that mean? To determine the line to line voltage, we will be finding the sequence quantities of the currents as well as the voltages. Then by using those things, we will be finding the line voltages VA and VB and VC. All these voltages will result into per unit. Then you have to convert those per unit quantities into the actual values by using the base value, that is 13.8 kV. Then you have to multiply all the per unit values with respect to the base values and convert to the line voltages. That is first method. Second method is convert all these per unit reactance values in terms of the ohms. Then everything will be in terms of the actual units. Then finally you will get all the voltages in terms of the kilovolts directly. In the final stage, you no need to do the conversion of 3 voltages. Instead, initially only we will convert all these reactances values in terms of the ohms and use those values for the calculations. I feel that is bit easy as compared to the first method. Now let us proceed. Base values. We know MVA base is given as 20 MVA. kV base is equal to 13.8 kV. This can also be represented as a 1 per unit if you want to find the values in terms of per unit first. Now, we need to find out the X base value. We know the formula for X base, that is kV base square divided by MVA base. We have seen in the last problem also. That is 13.8 whole square divided by 20, which will give us 9.522 ohms. Therefore, x1 in terms of ohms is equal to x in terms of per unit into x base value. That is equal to 0.25 into 9.522, which will give us 2.381 ohms. Similarly, you can convert x2 in terms of ohms is equal to, this is x1 per unit, and this is x2 in terms of per unit into x base value. What is the x2 per unit value? That is 0.35. 0.35 times of 9.522 will give us 3.3327 ohms. And x naught in terms of ohms is equal to x naught in per unit is 0.1 into x base value, that is equal to j 0.9522 ohms. Now the single line to ground fault. Now the given problem is with respect to the LG fault. Now we need to find out the fault current. Let us draw the interconnection of the circuit. So plus minus, this is EA and this is x1, x2 and x0 value. And we know IA0 is equal to IA1, that is equal to IA2, EA divided by root 3. Now let us mark the value. X1 is equal to J 2.381 and this is J 3.3327 and this value is J 0.9522 ohms. So this value will be equal to J times of x1 plus x2 plus x0, that is equal to EA value 13,800. It is 13.8 kV. 13,800 by root 3 times of J. If you add all the three reactance values, we will get 6.6659. That will give us J 1195.25 amperes. Therefore, subtransient fault current is equal to 3 times of IA0 for the line to ground fault. We are interested only with respect to the magnitude for the fault current. So that will be equal to 3 times of 1195.25, that is equal to 3585.25 amperes. So that's it. That is the first part of the given problem. And the second one is we need to find out the line voltages. For that, first we need to find out the sequence components of the voltages. What are the sequence components? What is the voltage measured across the positive sequence voltage VA1 and what is the voltage measured across the negative sequence VA2 and the zero sequence voltage VA0. So these voltages we should find out. We know VA1 is equal to EA minus IA1 into Z1 and VA2 is equal to minus IA2 into Z2 and VA0 is equal to minus IA0 into Z0. In place of Z, we have a reactance. Directly you can substitute in place of Z1 the reactance value. What is the voltage given? We know the voltage 13,800 by root 3. That will give us 7,967.43 minus the IA1 value just now we have determined, that is minus J 1195.25 into x1 value is nothing but J 2.381. So if we simplify this, we will get 5.121 kilovolt as VA1. Similarly, the minus IA2 into Z2 minus all the sequence currents are same into the Z2 value is equal to J 3.3327. We know that J into J square value is minus 1, minus into minus will become plus, then that will be directly you can multiply these two values which will give us 3.983 kilovolt and the VA0 value is equal to minus J 1195.25 into x0 value J 0.9522. This will give us 1.138 kilovolt. These are the sequence components of the phase voltages. Now we need to find out the sequence components of the line voltages by using the relation between the line and the phase quantities of the star connected system. Now the sequence component of line voltages, the positive sequence component is equal to J root 3 times of VA1. J root 3 can be written as root 3 at an angle 90 degrees into the VA1 is equal to 5.121 kilovolt. That is equal to 8,869 at an angle 90 degrees. Now coming to the VA2, that is minus J root 3 times of VA2 minus J root 3 at an angle minus 90 degrees and the VA2 value is 3.983 kilovolt. That is equal to 6,898 at an angle minus 90 degrees. And we know the zero sequence component of the line voltages will be always equal to 0. Even though the zero sequence component of the phase voltage present, but always the zero sequence component of with respect to the line voltages will be equal to 0. So directly we can take VA naught value as a 0. Now we have got all the sequence components of the line voltages. Then directly we can find out the line voltages. We know VA is equal to VA naught plus VA1 plus VA2. And if you substitute anyway VA naught value is equal to 0, if you substitute the remaining two values, we will get 8869 at an angle 90 degrees. 90 degrees can be written as J 8869 because we are doing summation here. For the summation, it is easy for us to if you use the rectangular forms, and it is 6898 volts. This can be written as J 1971 volts, that is equal to 1971 at an angle 90 degrees volts. Now coming to the phase B voltage, VA naught is anyway 0, that is equal to A square. VA naught plus A square into VA1 plus A into VA2. So here also VA naught is 0. A square value is 1 at an angle 240 degrees into VA1 value. VA1 value we know that is 8869 at an angle 90 degrees plus A value is 1 at an angle 120 degrees into the VA2 value is 6898 at an angle minus 90 degrees. That will be equal to 8869 at an angle 330 degrees plus 6898 at an angle 30 degrees. So if you convert this into rectangular form and simplify again, convert back to the polar form, we will get 13,690 at an angle minus 4.127 degrees. Now coming to the BC, VA naught plus A into VA1 plus A square into VA2. So this is anyway 0, A 1 at an angle 120 degrees into VA1, 8869 at an angle 90 degrees plus 1 at an angle 240 degrees into 6898 at an angle minus 90 degrees. So if we simplify this, we will get 13,690 at an angle minus 175.87 degrees. Now let me explain you the concept. Now let us consider this as a phase A, phase B and the phase C. Now fault has occurred between one of these phase to the ground. Then how to identify between which phase to the ground the fault has occurred? Means if you look at these voltages, we know that in case of shunt faults, the voltage will decrease and the current of that phase will rise. So if you look at the voltages of these phases, VA value is 1971 volts and VB value is 13,690 and VC value is 13,690. For us, the given line voltage is 13.8 kV. Yes or no? The rated voltage of the system is 13.8 kV. The phase B voltage is 13.69 kV and phase C voltage is 13.69 kV. That means these two values are close to these rated values. But if you look at the phase A voltage, it is only the 1 kV. Where is 1 kV and where is 13 kV? That means the fault has occurred with respect to the phase A. Because of one phase has short circuited, that phase voltage will dip and the current will rise. Because of the fault, these two magnitudes also will reduce from the rated voltage 13.8 kV. And the magnitudes, if you see, these all three voltages are supposed to be 120 degrees with each other. Because the system has moved to the unbalanced condition, these magnitudes also will be different. One is at 90 degrees, another one is at minus 4.127 degrees and another one is minus 175 degrees. What does that mean? Because of that single line to ground fault, system has moved to the unbalanced condition where all the line voltages magnitudes will be different and the phase angles also. So this is how you can understand what is the effect of these fault and the fault current with respect to the system, how the voltages are changing. Sorry, we are not supposed to draw like this. What is this? Only phase A to the ground fault occur like this. But even though the two sections are healthy sections, because of this fault, there will be some effect on the phase B and phase C also. This is how you should analyze the system under fault condition. I hope it is clear. Thank you.